starting right now. So I'm just checking that the streaming has good audio, and it should be streaming now. The URL is pre-shared today, so I don't use up class time to copy and paste the URL. So now we are ready to go. So we get a little bit more class time. So what we'll do today is to build upon what we have already introduced on Tuesday, which is the kind of the sub-circuit of adding. So what we'll do today is to look into how do we build a circuit based on the equations that we have that I have already introduced on Tuesday. So it's important that you kind of read ahead of me a little bit, and also study what we have already gone over, because otherwise this stuff is going to look pretty foreign. Okay? But if anyone has any question about base conversion or the older topics, it's fine. It's okay to bring those up in class as well. Okay? Plus, we also have plenty of lab time after class, so you can also ask those questions later on if you want to. All right. So in terms of where we are in the notes, we are still in binary addition, and tonight's lab is going to be multi-bit stuff, and also 3x3 look-ahead adder part 1. So there will be both of those kind of turn on at the same time. You want to do those in this particular order, so don't skip and work on the 3x3 carry look-ahead adder first, because that would not work at all. All right, so we'll go back to binary number addition, and I open it in a new window, so it's easier for me to switch around. I can just Alt-Tab and switch. All right. So let's go ahead and review some of the stuff that we have already talked about. And I'm going to use Notepad or Mousepad for this purpose. All right. So we got two numbers. Okay, we are adding x and y, and we want to get to the sum of those two numbers. So as it turns out, I looked up today. There's a special name for x. X is called an what is it? Gosh, I cannot remember. I think it's called an augend, okay? A-U-G-E-N-D. And then y is called an addend, A-D-D-E-N-D. And then s is, of course, the sum. So, so if you want to refer to those in very specific terms, you can look them up. One is called augend. The other one is called addend. Okay, I'm pretty sure that's not how it's properly pronounced, but if you just kind of spell it out, that's kind of what they sound like. So you can see, augend is the first number, and then the addend is the second number, and then the sum is the result of the calculation. But in this class, we'll just call augend x, we'll call addend y, and then we'll call the sum sum. Is that okay? All right. When we get to subtraction, we'll actually use the proper terms, but for addition, we'll just use x, y, and then sum. Okay. So knowing these terms, we can now specify the bits, okay, how each bit is calculated. So if you want to look at q, okay, now q is the partial sum. So q of I is the result of adding xi and yi. Now this is nothing new. It is in the notes as well. So if you have reviewed the notes, in the notes I do not use square brackets because it's easier for me to type with subscript in the notes. So if you see something like x subscript I in the notes, if I use a notepad, sometimes I would use square bracket so that you can see that it's just indexing into which bit we are talking about. Okay. There's k. So k is the complicated one, because ki plus 1, okay, now this is I plus 1, because you can only determine the carry of the next column using the current column, okay? So you cannot determine the k of the same column as the other ones. So we have two carries, okay? The first carry is coming from adding xi and yi. And then the second carry is coming from adding qi and ki. And these two are now added using a regular addition. Okay, so this plus is not a disjunction, it is an actual addition. Are we good so far? And then the sum is pretty easy to figure out. Okay, so the sum, which is S subscript something, is really just the partial sum of the Q and the K. So it's Qi, Ki. And if you look at the partial sum of Q and K, that becomes our sum. Are we doing okay so far with this? All right? And then we also look into the truth tables, okay, and we find out that R is just exclusive OR, okay? Because when you work with binary numbers, xi is only a 0 or 1, yi is also just a 0 or 1. So the function that we need to do to figure out the partial sum can be implemented using logic gates or Boolean operations. Okay, so R of, okay, I'm going to use another set of symbols here. Let's say, I don't want to use A, B, C, D, E, F, G, H, okay? H, I, J, K. I'm just going through all the letters because I want to find one that is not used already in my notes. W is not used. I think V is used. U and W. Okay, there we go. Okay, so if you look at R of UW in base 2, okay, this only works in base 2. It is defined as U and, okay, I'm going to spell out the whole thing, but in time I will kind of make it so that it is not going to, I'm not going to spell out the entire thing. And then this part is not U and W. Okay, it's just exclusive OR. But instead of using exclusive OR as one single operator, I am boiling it down to operators that we already know. Okay, we have conjunction, we have negation, and then we have disjunction. Okay, so you don't really have to write this stuff down because it's already in the notes. It is already in the notes, the definition of R. This is just a recap of what we have talked about last time. So the carry bit is even easier. The carry bit, is really just U and W, logical AND. Because the only time you have a carry of 1 in a base 2 addition is when you have 1 plus 1. You don't have a carry, you have a carry of 0 for the other 3 cases. 0 plus 0 has a carry of 0. 0 plus 1 has a carry of 0. 1 plus 0 has a carry of 0. Only 1 plus 1 has a carry of 1. So it's easy. You just use conjunction to figure out, do we have a carry of 1 or not? Is that okay? So once again, this is all in the notes. I'm just doing this as a quick recap of what we have already talked about last time. Okay? Now, if you say, yep, I'm reconnecting with everything that we talked about on Tuesday, great. Okay? On the other hand, if in your mind you're going like, I have no idea what this is all about, okay? Then we have to figure out a way for you to kind of work more efficiently. Maybe study a little bit after the class, okay? Maybe reviewing the material a little bit before this class. But we have to do something if that is the case. If people are telling me I have no idea what this stuff is, then we need to kind of refine the studying, study habits, or how people study. It has nothing to do with how hard people are studying, so I'm not judging people and say, nah, you guys are not studying hard enough. It has nothing to do with how hard we're studying. It has to do with how we are studying. Okay, so that's a difficult thing to teach, okay, but you basically have to make sure all the concepts are cleared in your head. You're making connections between everything in order to kind of move on in this class. So are we doing okay so far with these? Are we reconnecting to the topics on Tuesday? Yes? Okay, excellent. So when you look at all of these equations, you can go to Q of I and say, oh, that's pretty easy to do. I can just build a simple circuit. Okay, we'll take Xi, we'll take Yi as input pins, and then we plug it into something like this, turn that into a logic sim, gate logic thing, and then the output is going to be Q of I. So I'm going to show you how we can do this, okay? Because in previous semesters, some people cannot associate equations or expressions that is expressed like this to how the gate should be connected. So we'll do a quick one just so that we know how this is done. Okay. All right. So I'm gonna go get Logisim started. So it's java-jar, and I have to remember where I put mine. I think it's here. Yep. And we are going to, I'm going to recap the equation here. Okay, so we'll say R of UW is, and this time I'm going to use a shorthand. So it's going to be the negation of U and W, or the non-negative version of U and the negation of W. Can everybody see the text? No? Okay. How about that? Is that good? Okay, cool. All right. Oh, right, instead of exclamation point. Okay. There you go. All right. So now we want to build this circuit. So this circuit has how many input pins? What do you think? It's got 2 input pins. Okay. It has got 2 independent variables, U and W. Okay. And how many output pins are we talking about? 1 output pin. Very good. Okay, so we'll place the pins first. Now, when you use input pins and output pins, my recommendation is to use the ones already on the toolbar. Okay, you can get those from wiring as well, but there's a difference. If you get them from wiring, they have a 3-state enabled, which we do not want to use in this class. So instead of having to turn all the 3-state to disabled, it's just easier to pull it from the top. And then we have this as U, okay? And then we'll pull another one as W. There we go. All right, so now we got 2 input pins. The labeling is just so that it's easier for us to figure out which one is U and which one is W, okay? But since the expression is somewhat symmetric, it really doesn't matter which one is U and which one is W. And then we'll also place an output pin, which is this one here. And we'll just say that this is the result of those 2. So it's the result of U added to W. It's the partial sum, okay? So now we have the input pins and the output pin. The pins of a circuit are analogous to parameters of functions in C and C++. Because they are supplying, okay? Some are supplying information for the computation, and the other ones are for capturing the result of the calculations. So when you look at pins in the circuit, they are basically parameters. Okay, so now the question is, what do we do to connect these 2? Well, we look at the equation. We look at the expression. The expression says, the final operation is an OR, okay? So if I want to be a little bit more specific, okay, we can go back here, and if we are not clear about the priority of the operators, I can add additional parentheses to emphasize that. Now, it's because at the beginning of the semester we are not quite familiar with the priority of operators. I'll do this, but later on in the semester I'm not going to use additional parentheses. Okay. All right. So with these, what kind of gate, okay, the output of which kind of gate would go straight to the output pin? What do you think? The OR. The last operation is an OR. So you go to, not wiring, you go to gates, and then you pick out a OR gate. Okay, you can do it this way. You can also go to here and pick out the OR gate like this. Okay. Now, if you look at these symbols and go like, I have no idea which one is an OR gate, which one is an AND gate, well, they are kind of spelled out here, right? So you can look at the names of the gate and look at the symbols. If you are planning to become an electrical or a computer engineer, you have to learn these symbols anyway. Okay, they're just important in those 2 subjects of study. So in this case, we have a 5-pin OR gate, and you look at the properties and go like, well, we don't need all 5 gates. I just need 2. Okay, so shrink it to 2. And also, you look at the size of the gate. It looks way too big. It doesn't need to be this big. And you can shrink the size to narrow. So this is really just so that it looks nice, okay? It's not necessary, but it's good to make it look nice, like that. Okay. And then what do we need? We need some AND gates, okay? Very good. So we'll go ahead and pick out an AND gate here. Same deal, it is 2 bit, it has got 5 inputs. So we shrink 5 inputs to 2, and then we shrink the shape from medium to narrow. So now we have an AND gate. Now, if you have a gate and you say, I'm going to need one or more of these, okay? You can Control D for duplicate, okay? So once you have something selected, it can be a multiple selection. You can select multiple things. If you press Control D on the keyboard, it will duplicate the entire selection. So that's a really handy way to have multiple things, or things that you have already configured, and you go like, I just need one of those, or one more of those. This is a good shortcut to get it done for saving time. Okay. So now we have 2 AND gates, and we know the AND gates feed directly to the OR gate, because you can see how the result of the AND and the result of the AND here are directly feeding into this final OR gate. So we just connect these lines. Okay. All right. So now we know we have to negate U to bring it here, and then bring W non-negated over here. We have to bring U non-negated over here, and then bring W negated over here. There are 2 ways to do it. One way is kind of more tedious. The other way is like super nice. Okay. So the tedious way to do it is to pick out a NOT gate over here. So there's a NOT gate, which is the first one. So I can attach a NOT gate to the input of the AND gate in order to negate one of the signals. Okay. So that's one way to do it. But the other way is to look into the properties of the AND gate, and you will see that in all the gates, okay, except for NOT gate itself, there are 2 properties here with a very interesting name. Okay, so I'm going to expand it a little bit so we can see the actual description of those properties. So the top one says negate 1, the top pin. The second one says negate 2, which is the bottom pin. This is a great, easy way to negate an input to an AND or exclusive OR gate, because you can just negate one of them. So let's say we want to negate the top one. You just have to say, do we want to negate? Yes. And now you see a bubble. That bubble tells you that that pin, that input pin, is negated. If you give it a 1, by the time it's presented to the AND gate, it will be a 0. Are we good so far? All right. So it's a shorthand to, instead of actually using a NOT gate, this is a lot, I think it's a lot easier. So this one would be the bottom one, like so. So now you just have to bring this one to the first pin of the first one, and also the first pin of the second one. Okay. And then you take this one and do the opposite. It goes to the second pin, and also, okay, I overshot a little bit. It still works, it just doesn't look good. There we go. So now we have exclusive OR. So once you build a circuit, okay, the next thing you want to do is to test it, okay? Is it really exclusive OR? Well, fortunately, with Boolean values, we can actually exhaustively test every single case. So we have 0 exclusive OR 0, which is supposed to be a 0. So we are good. So to test a circuit, you have to change to what is called the poking tool, or the little finger tool. So now we have 1 exclusive OR 0. The output is a 1. That is correct. And then we have 1 exclusive OR with 1. The output should be a 0. We're good. And last of all, we have 0 exclusive OR with 1, and the output is supposed to be 1. So now we have just exhaustively tested this circuit, and it just does whatever exclusive OR is supposed to do. It is kind of cool. Do we have any questions at this point? Because the main point of this exercise is so that I can illustrate how you can look at the expression and turn that into a circuit. Are we okay with those concepts? Are we good? All right. People in the back? Okay, you guys are all good? Okay, all right. So we have just built exclusive OR. Carry is just an AND gate. We're not going to build it. We will just use the internal one. And because this is really just exclusive OR, if you want to, you can just go ahead and use exclusive OR gate, okay? Because it does exactly the same thing. Okay. All right, so let's go back to mousepad. We look at this mess here, and we look at each one and go, do we know how to do this? How about this one? Pretty easy, okay? So xi and yi are input pins, okay? Because the number that the two numbers that are provided to you, remember one is called the argand and the other one is called the addend, okay? Those two are given to you, so they're presented to you as input pins. So these are just pulling things out of an input pin, and you have to go through the gate that we just looked at in order to come up with the queue of i's, okay? So that's not a problem. So if that is not a problem, this one doesn't seem like a problem either, right? Because it looks kind of the same as the first one, except it will take Q of I and K of I, go through that circuit, and then we end up with the actual sum bits, which is the result that we actually want. So we don't have a problem with that. The one that has a somewhat of a problem, two problems, is this one here. Because you can see how ki plus 1 depends on k of I. See how ki plus 1 is on the left-hand side, and then k of I is one of the things that it depends on. So what that means is if you want to figure out what is ki plus 1, you have to first figure out what is k of I first. If you want to figure out what is k of I, you have to first figure out what is ki minus 1. So it has a chain dependency. We doing okay so far? Does everybody see the chain dependency? That's one problem. The second problem is that plus over there, that's an actual plus. It's not an OR. Okay, let me highlight which one we are talking about. This is an actual arithmetic addition. It is not a logical OR. We want to turn that into a logic gate too. Yeah? We are talking about binary addition, but in order to say that this is just a regular OR, you have to make sure that this and this, they cannot both be ones at the same time. Because if they're both ones at the same time, then arithmetic addition and logical OR will give you different answers. Did we talk about why they cannot both be ones? I don't think we did. I talked about it during the lab time because somebody asked me about it, but I don't think I used lecture time to talk about it. Yeah? I did? Yeah. Oh, okay. So since we know they cannot both be ones, then we can replace it with an OR, a regular logical OR, and we're all good. So this solves one problem, but it doesn't solve the problem of ki plus 1 depends on k of I, and then it just chains itself all the way back to k of 0, which is assumed 0 most of the time. Are we doing okay so far? Yes? Okay. So what I'll do today is do one of the ungraded assignment, if you look it up, which is building a carry ripple adder, okay, before we start to talk about carry look ahead. In other words, I just use these equations and I'll come up with an actual adder circuit that works, okay? But it has a problem, and then we'll talk about the problem later. So I'm going to pull this to the side. And I'll put this to the corner here, and we'll just refer to it occasionally. And in here, I'm going to add some circuits. So in the project, I can add a circuit, give it a name, and this one is called a half adder. Okay? So what a half adder is going to do is to handle one part of the adding. Okay, let me go back to the table view of how we perform addition. So let me just kind of go through one example of binary addition, and then we'll that will help us clear up a little bit of stuff. So we have 1, 0, 0, 1 plus 0, 1, 1, 1, okay? And we want to see how this is done. If you have any questions, about this example, you really should ask questions right away because the circuit depends on, this part here. So we already know this is what we call X, which is also called the argand. This is what we call Y, which is also called the addend. This part here has no specific name, so I'll call it Q. This one here has no specific name other than those are the carry bits. We'll call it K. And this is just our sum. So you will hopefully, you're starting to remember, how I name each row. Okay. So this one is just the R of 1, 1. Okay. So 1 exclusive OR with 1 is a 0. This one here is 0 exclusive OR with 1, which is a 1. This one is 0 exclusive OR with 1, which is a 1. This one is 1 exclusive OR 0, which is also a 1. Do we have any questions of how I filled up all the bits on the row of Q? Okay, we're just applying exclusive OR on XY. Okay, that's easy. This one is easy too because we just assume K0 to be 0 because it is the least significant digit and nobody is carrying over to bit 0. Okay, so we assume that's 0. So to figure out this particular carry bit, we have to ask two questions. The first one is adding X and Y in the previous column or the column to its right-hand side yield a carry of 1? The answer is yes. Okay, so it is a 1 already. I don't even have to bother to look at adding Q and K because once it is a 1, it cannot be anything else. What about this one here? Okay, so this one depends on, well, if I add 0 to 1, does that give me a carry of 1? No, it's good. If I add this one to this one, does it give me a carry of 1? Yes, okay, so I have to put a 1 over here. And then this one is kind of the same, in the same boat, right? So it's going to be a 1 as well. And just for the sake of calculating the overall carry, what about this one? Yep, it's going to be carry of 1. So now we can compute the sum bits. The sum bits are pretty easy because it is the exclusive OR between the Q and the K. And we have all the Q and the K already at this point. So in this case, it's 0 exclusive OR with 0, which is a 0. 0 exclusive OR with 0 is, 1, 1 exclusive OR is a 0. 1 exclusive OR with 1 is a 0. 0 over here. And this one, yeah, we'll just leave it hanging on, like that. Okay? All right. So the idea of presenting this picture is because I want you to see how these 3 bits, okay, how we use these 2 bits to come up with this bit, is a half adder. That is half adding. And then we take these 2 bits to come up with this bit. That is also the same mechanism. It's also half adding. So go ahead.
Then we just need, so we need the half adder, we use it twice, and then we need another thing to figure out carry bits.
Yes.
That's it.
Yep. So because the mechanism of adding xy to come up with q and the mechanism of adding qk to come up with s are the same, it makes sense to make a half adder circuit so that we can just use multiple instances of the half adder circuit in this design. Is that okay? All right, so that's what we'll do next, okay? We'll build a half adder circuit. So the half adder circuit really doesn't have much to do. It has to do the exclusive OR, right? And then it has to come up with a potential carry bit when we add these 2 bits. So it has to compute the R, it has to compute the C, the carry, and that's it, okay? So we'll go ahead and build that circuit in LogicSim. And I'm going to cheat a little bit and use an exclusive OR gate instead of that complicated version of exclusive OR. So this way the circuit kind of looks nicer. Okay, 2 inputs, narrow, okay. And then we have, I'm not going to call these xy anymore, okay. Instead, let's call these the proper name, okay? So one is called the augend, and then the other one is called the addend, okay? So we take these two, okay, move this one up a little bit so it looks nicer, like that. And then the output of this is what we call R. And we'll just label this as R here. Okay, do we have any question? We're going to have, yep, we'll do the carry. So this time I'm going to switch the order around a little bit, and we'll label this as our carry bit, which is C. And do you remember which logic gate we should use to compute carry? Logical AND. Okay, very good. So we use logical AND. And I should have just copied the other one. And by the way, you can switch between the circuits just by double-clicking. So if I want to go back to the main circuit, which has the nice-looking smaller AND gate, double-click, go here, Control-C, go back to half adder, and then Control-V, and then move it, and then fix the negation input, because this time I do not want a negation on the first input. And now we have a regular logical AND. And then we make some connections, like so. And we have a half adder. Okay, so this is what we call a half adder. We have one output being the partial sum or the result of adding 2 bits, and then we have another output, which is the carry of adding those input bits. Do we have any questions? No questions? Go ahead, ask anyway.
So I'm just trying to, I can't figure it, I'm trying to look at the circuit in my head. I'm trying to figure out how we're going to use the carry bit, how we're going to.
Aha. Yes, I will answer the question.
That's what I figured.
Yep, I will answer the question. But because it's a good sign that you're thinking about it, because that when I talk about the answer, then you will make that instant connection right away, because you're already almost there, right? Okay. So, but before we move on, we have to give this circuit an appearance. So we go here, and then we switch to the circuit appearance like this, okay? So these two views also have analogies in C++ or regular C programming. This view is more like the prototype of a function, where you only look at the name and the parameters and the types of the parameters of a particular function. The other one is looking into the definition of a subroutine, where you see everything, including the implementation of the function. So that's how these two things are related. So switching here, if you want to say, I better label these pins, because after today, I won't be able to remember which one is which one. So what you do is you click on one, and you can see how at the lower right corner, you have a PIP, a picture-in-picture, and it highlights the corresponding pin in the circuit. So that helps you to identify which pin is this one. Oh, that's the augend, okay? And then, so that makes it easier. And you should try to label the pins as much as you can. So I'm just going to use AUG here, because both of these will end with END, okay? And then this is R, and this one is C. This is typically how I do it. I just kind of place the labels approximately where they are needed. And then you can go ahead and switch to the pointer tool. And then you can move things around until you say, yep, this is exactly where I want everything. Okay. There we go. Okay. And it also helps to add some documentation for this circuit itself is a half adder. It's not 100% necessary. It is just I like to do it here. Okay. Or you can put it inside the box. It's up to you. Do we have any questions about this particular view, what it does, and why I label the pins? Yes.
So I just wanted to ask, so if the inputs are both 1, then it goes to the carry part, and then the carry will be 1?
So if both inputs are 1s, then the carry is going to be a 1. The result is going to be a 0.
And then if either one is a 1, if one is a 1 and the other is a 0, then
Uh-huh.
the carry would be a 0, and then the result would be a 1, right?
Yes.
Because
Yes.
And then the result goes through an exclusive OR gate.
Yes.
What if they're both zero?
Well, 0 exclusive OR with 0 is also a 0, and then 0 and 0 is also a 0. So if you have both inputs being zeros, then both outputs would be zeros as well. Okay? All right. So now we have a component. And then we can go to a full adder. Okay, so we go to project, we add another circuit, and we'll call this one our full adder, which is responsible for one column when I use mousepad. Okay, so let me switch back to mousepad first so that we have a reference of what we're talking about. So this is one half adder. Okay, this is another half adder. This entire thing is one full adder. Is that okay? So you have to first think about how do we connect the two half adders to a full adder, okay? So we can see how the R, which is this one here, of the first or the top half adder becomes one of the inputs. In fact, it becomes the argand of the second half adder of a full adder. Is that good? Okay? And then the carry from a previous column becomes the addend of the second or the bottom full adder. Are we good? Now, what is not shown here, okay, is the carry of these two bits, adding these two bits, and also the carry of adding these two bits. They are joined by OR before feeding into that bit. Okay? So that part is a little bit tricky, but we'll get to it at some point. Yep.
One thing, the one thing that I'm questioning right now is there a way to do this without just chaining a bunch of half adders together?
Yes.
Okay.
And that's why we have the carry look ahead mechanism. But I want to introduce carry ripple first so that we can see the problem of this approach. Okay? All right, so getting back to LogicSim, I can now implement a full adder using two half adders. Does that make sense? You know, having two halves make a full. Okay? So if you want to use a circuit that you have designed in the same circuit file, just single click, not double click, okay? Single click on the component that you have created and then drag it over here. So this is kind of the same thing as instantiating objects out of a class. Okay, so when you look at all the circuits listed here, these are all classes. The moment you single click one and put it into the actual circuit, you have just instantiated one and put it into the circuit that we are building at this point. Kind of as a local variable, okay? If you want to equate it to terms in C++ programming. So we know we have two of these, okay? So we have two of these things first. So now remember, we are talking about one full column, okay? So we want to be able to label X, Y, Q, K, and S, okay? All right, so X, Y are input pins, so those are fairly easy to deal with. So we got, okay, the first one as X, okay, and the second one as Y, and they correspond to the argand and addend of the top half adder. So that's pretty easy to connect, right? It's just a straight across, like so, straight across, like so, and we are done. Are we good? What is the output? What is the R of those two? That's our Q, right? Yes? So this is the first semester when I introduced tunnels early on in the class, okay? So a tunnel, okay, let me show you what a tunnel looks like. It is a part of wiring. This is what we call a tunnel, okay? So a tunnel is interesting because what it does is it allows you to connect, it allows you to break a wire into various points, okay? So I'll show you. The best way to illustrate is to show you. So I'm going to label this one Q. Now, with everything else, the labeling is not really that important. It's just documentation purposes. But with a tunnel, the label is important because all tunnels of the same label are logically connected in the circuit. Yes?
So you should think of the tunnels as like a radio transmitter that's transmitting a specific frequency. So if I've got one tunnel input, so like what you got there, labeled Q, and I have a bunch of tunnel There are one transmitter and a bunch of receivers on the same frequency.
They are basically connected to exactly the same, what we call the same net in terms of a circuit design. So with this one, I would need to change the phasing first because the pointy end is where the phasing is, which is also where the connection point is. So this is another thing that you have to pay attention when you draw circuits like that, because of the entire thing, there's only one point where it is making a connection logically. Okay, so you have to know where that point is, because if you point it, if you draw a line and it connects to any other place of the same thing, it doesn't actually make a logical connection. You have to connect to the pin of that device that actually allows the connection. So we know Q serves as the argand of the second half adder because it's the Q, right? Okay, let me go back to mousepad. You can see how the R of XY is this pin here, right? But this is actually the first item to add of the second half adder. Are we making that association? Is that okay so far? Yes? Okay. Are we all okay with that? Yes? Okay. So I'm looking for a conjunction of yes of the class, when I ask you, are we okay? Because if I use an or, that means if at least one person in the class understands the concept, I get to move on. That may not be a very good way to conduct a class. Only relying on at least one person understanding, then I'm good to go again. So I'm kind of trying to do a conjunction here. But when people do not nod, when people do not give me any indication, it's kind of like an X or unknown. Okay, so getting back to the circuit, okay? What about this guy here? What is it supposed to be? Oh, it's supposed to be K. All right. So we'll make a pin, and we'll call it K. Now, K is a pin, it's not a tunnel because it has to come from outside. It is not coming from within the circuit. Q is just a tunnel because we are just bringing one part of the circuit to another part of the circuit. And I label Q just so that it goes back to mousepad. It goes back to the expressions that we have talked about. Are we still doing okay so far with this? Okay, yep.
So then we're going to make this into a circuit. And then if we wanted to add a multi-digit binary value, we're then going to just have a bunch of D's.
Yep.
And the C's are going to be ORs, and they're going to output to the K.
Well, the OR is going to be here. So I'm not quite done because the outputs are kind of not connected right now. Yeah.
We're putting a C here before we finish, or an OR of these two C's, and that's going to output to something.
Yes.
And then that's going to go to the K.
Yep.
Next.
Yep. Exactly. So, but the first thing we want to do is to do the simple one first. Okay. Where does this go? It goes to S, and S is it a tunnel or is it an output pin? It's an output pin because somebody from outside needs to know about it. It is not an internal thing. It is the actual result, right? So we want this to be an output pin. Okay, fine. We'll do an output pin and put it here and label it as, and we are done with that. Okay. So now we have two mystery output pins from the half adders, and they're just kind of dangling. Okay, the carry bits, right? So we know these two carry bits need to be ORed, and it becomes the carry bit of the next column. Okay, so now we need to kind of do all that part, right? So we need to bring an OR gate, and I think I got one in the main circuit. Yep, so we take this, Control C, go back to full adder, paste, and okay, and then we hook up these two. Okay, this is one. This is the carry of adding XY, and this is the carry of adding QK. And the output of this becomes a pin because it needs to be known by somebody outside of this circuit. It becomes an output pin. And how we want to name the output pin, we can call this carry out. Okay, so we'll say this is K out. I do know that carry starts with a C, but since we have been using the symbol K, so I'm going to use K out instead of C out. Are we good? So the other one is actually technically K in, so we'll go ahead and add the in here so that the pins are self-documenting. So now we have a full adder. And once we have the circuit done, we probably want to make the appearance, the circuit appearance, look nice, okay, and kind of make it easy to daisy chain, okay. So now we have this. If I don't do a single thing, this is what it's going to look like, which is kind of difficult to read because we don't know what is what. So we'll go ahead and do some labeling, okay. So we got X, we got Y, and this is carry in. This one I cannot remember already, but that's okay because we can click on it. Oops, nope, come on, there you go. So this is actually our carry, not S. The reason why that is the case is because it depends on the positioning of the circuit. If that is not where you want it, okay, so let's just say that you want this one to be the S pin and you want this one to be the carry pin. It's okay. You can move those around. Okay, so you can just kind of click on this one and drag it out, and then you click on this one. Not that, yeah. Move it down. You can even move it down one more. Okay, if you want to make it look kind of nice and square, and then put this one back here. Okay, so I have moved the pins in the appearance, but I haven't really moved the pin in the actual circuit definition. Yes. You mean this line here? That is the home position of the entire quote-unquote chip. So, so the chip has its own little home position. So when we refer to the location of the circuit appearance, that is dictating that. It's also dictating the facing. So this way, the circuit right now is facing east. This is what it looks like facing east. So when you change the facing, you're changing orientation of that line. Okay, so I better label these two pins and making sure that this one is our carry out. Okay, so we just say this is our K out, and the top one is our sum. There we go. So now we can just kind of clean up the positions of the labels a little bit. For those people who have OCD, they can spend like half an hour doing this. I'm particularly sloppy, so it just takes me a few seconds to do it. There we go. All right, cool. So now we can move on to talk about the multi-bit thingy, okay? So we can go to, we can do a 3x3, okay? So we can say 3x3, this is what we call carry ripple adder. And I'll explain why it's ripple, okay? It'll be clear once we build the circuit. So the first thing is we need to have an input pin for X, an input pin for Y, an output pin for S, and an extra pin, single bit pin for the overall carry of the 3x3 adder. So we'll go ahead and pick up some pins, and it's okay that these are single bit to begin with because we can change those later on, okay? And so we have 4 pins, but this one is our X, which is multi-bit. It is a 3-bit thing, so that's okay. We can go to data bits, change it from 1 to 3, and now it becomes a 3-bit input pin, okay? It's one single pin, but it has 3 individual bits. We do the same thing with Y. It's 3 individual bits. The same thing with sum. It has 3 bits. And then this is our overall carry. So we'll just, we can call this K out again. Okay, so now we have defined all the input and all the output. How many full adders do you think we need? 3, very good. Question? Oh, just indicating 3. Okay, very good. So we have 3 of these, okay? Copy and paste. Okay, we got 3 of these. Now, the relationship between these 3, we know kind of how to do this already, okay? So let's just say that this is responsible for bit 0, this is responsible for bit 1, and this is responsible for bit 2, okay? We'll make that assumption. The carry bit of bit 3 goes straight to carry out, okay? That's pretty easy. there's an error because there are no inputs, and if there are no inputs, it cannot do any type of actual gate computation. So it's okay for it to have an error at this point. Not a big deal. We also know the output of one bit becomes the input of the other one. So we take this one out, and then we connect it to the input of the next one. We take this output pin. Now this is actually why it's called carry ripple, because you can see how it is forming a chain of full adders. This connection alone is causing what we call the rippling effect. Yep.
This is the same thing as we were doing with the tunnels earlier. Is there a particular reason to use tunnels or to do this over doing this, or is it just to make things look prettier?
I could have used tunnels to do this, but doing it this way makes it actually, it's visual, okay? You can visually see how the last full adder depends on the output of the second, and the second depends on the first. So until the first one is done, the second, they will all do computations all at the same time. The question is it correct? Okay, so all three full adders will do all their calculations all at the same time. But the third full adder, you cannot trust its output until the second full adder is stabilized. But the second full adder cannot be trusted until the first full adder is fully done with its calculations. Is that okay? So we are waiting for the carry bits to ripple through this chain in order for the result to be valid. That is why it is called a carry ripple adder. Okay? All right. So now we need to figure out, how do we get this to here, okay? And it goes like, uh-oh, doesn't work, because the pin has 3 bits, but the X bit of the full adder is only a 1-bit input. Okay, so that's not going to work. All right, well, if it doesn't work, we undo. So what we need to do now is to split a multi-bit thing into individual bits. Can anyone guess what type of thing we need to get it done? A splitter, all right. All right, so this is what a splitter looks like. Okay, well, there are multiple appearance. You can change how it looks like, and we'll need a 3-bit splitter that splits into 3 different things. So the one of your lab, has to do with the exercise of splitters. So what I want you to do, okay, because someone is going to ask me in the lab anyway, but I'm trying to reduce the number of people asking that question, is go through this entire thing first, okay? Look at all the properties of a splitter, okay? And you can see how each individual bit has its own little property. In other words, you can say, I want bit 1 to be here, or here, or here, or does not appear at the split end of the splitter. That's okay too. Because sometimes you only want one single bit out of a multi-bit wire, and a splitter allows you to specify that without the extra split end. Okay? But somebody's going to ask me that question anyway, I know that. That's just experience. All right. So now we have X split into 3 bits. This is bit 0 of X, bit 1 of X, bit 2 of X, and Y is split the same way into its 3 individual bits. So now it's just a matter of drawing the connections, the most boring part of making a circuit. All right. Sorry?
Someone's putting a bunch of keys in the door.
Oh. It's probably the janitor trying to get in. Somebody wants to use the classroom?
Want to clean it.
Oh, want to clean it. Okay. All right, so we're almost done. Almost done, okay? Because we need to figure out what this input bit is going to be. What do you think that should be? 0. Okay. And you can see that 0 is a constant. And we can pull a constant like this and change the value to 0. and stick that over here, make that connection. Almost done. What about the output? Okay, so we want to connect all the sum bits into here, right? Not gonna work. Okay, once again, we have a bit width, non-compatibility thing. And what do we need? Well, technically it's a merger. So what does a merger look like? You take a splitter and flip it around, exactly. So you can there are several ways to flip it around depending on how you want it to look like. So you can go to the property and you can say face west first. So now it's split. It's the split end is now to the left, and then the merged end is to the right. Okay, so that is sufficient for us already. So I'm just going to do it this way. So bit 0 is coming from bit 0 of the full adder. Bit 1 is coming from bit 1 of the full adder. And then the most significant bit, bit 2, is coming from the last one. Okay, we got our 3-bit by 3-bit carry ripple adder. Yes?
Should we use a four-way adder instead of having that output carry?
Say that one more time.
So if we're adding, let's say we're doing the addition that we did earlier, the 1001 plus 1110,
Uh-huh.
or 1111, whatever it was.
Well, that was a 4-bit thing, so we have to shrink it into 3-bit. But yeah, go ahead.
But the point is, if our output would have 4 bits,
Our output will have 4 bits, yes.
because there's a carry on the last adder.
But the carry is on its own. It is not a part of the result. It is not considered a part of the result. If you are talking about the 3-bit by 3-bit adder, the sum is always just 3-bit wide. The extra carry is on its own. It is an output, but it is not considered a part of the sum. Okay? All right, well, it's time to test this, right? So let's go ahead and throw some test cases in. We can have a 101 plus 11, which is 8, right? 101 is 5, 11 is 3, 5 plus 3 is 8. 8 is just out of the range of what we can represent using 3 bits. So the result would be 0, 0, 0 with a carry of 1. And is that what we're getting? Yep. We're getting 0, 0, 0 as the output with a carry of 1. Cool. Okay. So let's decrease it by 1. Okay. Get rid of this 1. So 101 is 5, 0, 1, 0 is 2, 5 plus 2 is 7. 7 is 1 plus 2 plus 4, which means it is in binary 1, 1, 1, and there's no carry. And we're getting that. So just by spot checking seems okay, right? Okay. But the idea of this circuit is to illustrate the carry ripple effect, because this guy cannot be trusted. This output here is not valid until this input is valid. But this output is not valid until this input is valid, and then this output is not valid until it has first it has gone through all the computation for the first full adder. So the bottom line of this is the wider you want to add, the more time it is going to take, and it is proportional. Okay, if you figure out a 4-bit by 4-bit adder, it's going to take 2 nanoseconds, okay, to get all the results, okay? Then a 64-bit adder is going to be 16 times that amount of time, because 16 times 4 is 64. So the longer or the wider the adder, the more time it will take to compute the result, okay? So is that really a problem? It is not a problem unless your competitor has a faster way of doing it, right? So let's say Intel looks like this and go like, this is simple, we like this, okay? And then AMD comes up with a better approach, which is called carry look-ahead mechanism. Then Intel cannot do this anymore. So even though this approach is very simple, and it doesn't use a lot of gates, we cannot use this, okay? I would not be surprised, okay, if you move on to a 4-year university in computer architecture or logic design, they talk about adders and this is what they tell you, okay? Because it's easy, it corresponds to the equations, but it has this fatal flaw of it's taking a long time to compute a 64-bit, adding to a 64-bit, okay? So what are we going to do? Okay, we have to break this dependency. So what we do is we go back to the notes. Okay, hopefully it is this one here. Okay, and then we go to the notes. Where is that? Nope, not this one. Oh, right, I opened it in a separate window. There we go. Thank you. All right, so it all has to do with section 6. Okay, section 6 is the one that talks about the dependency. So we'll look at this long chain of derivation here. Now, do I expect you to be able to do this? No. Do I expect you to understand this once I have explained it? The answer is yes. Okay, and some of you will see this type of derivations again in various other classes. Do we have a question about the first, this part here? Any questions about this? That should look really familiar by now. Because we talked about it on Tuesday, and then we talked about it today. And then we look at the circuit diagram, it has the same kind of structure. So that should not be a big surprise. Going from the first row to the second row, do we have any questions about that? I'm just converting all the C function into conjunctions. We know that works already, right? Okay? So what about going from here to here? Do we have any questions? What got changed? Qi got expanded. Okay, that's all. Okay, Qi got expanded. So Qi, which is here, is expanded to the R of xi, yi. Okay, we know that, okay, because that's how Q of I is defined. What about going from here to here? That's just a super lengthy way of saying exclusive OR, okay? How about from here to here? Distributive, right? Okay, so as it turns out, distributive works in both ways in Boolean algebra. Because in arithmetics, it only works in one way, right? A plus b in parentheses times c is the same thing as a times b plus a times c, right? But the other way around doesn't work in arithmetics. It does work in the other way in Boolean algebra. Okay? All right, how about from here to here? That one here, right? So this one here, remember one is true, and multiplication by one means and true. Okay? Can everybody understand why something and true is just that original something? Are we good? So true is kind of like the identity of conjunction, just like 1 is the identity of multiplication. Is that okay? All right, cool. What about the next row? The next row looks really kind of questionable, because I turned this one into true or ki. That doesn't work in arithmetics. Okay? In normal algebra, it doesn't work. But in Boolean algebra, it works okay. Because we are basically saying, is true the same thing as true or something? What do you think? What is true or something? True. It's always true, because if you have an or, if one side is true already, it is always going to be true. It doesn't matter what the other side is. Is that right? Okay? And then I distribute that, okay? So from here to here, I just distribute this 1 to here, which kind of disappears, and then ki goes here. So we take this, and it becomes that, okay? And then over here, we just replicate the term, and it has 2 copies of the n at this time. So we have this term here, and then we have this term here. Is that okay? If we have originally one single thing, let's say it's x, and then we say x or x, is x the same thing as x or x in Boolean algebra? Yeah, okay. So we can just replicate that thing and just move it around. It doesn't really change the equation. So at this point, you would think Tech must have gone out of his mind, because he started off with something simple and ended up with something that is a lot longer unnecessarily, so it seems, right? So now I do some moving around, okay? I group things by parentheses, right? So this is just kind of in parentheses grouped. This is now in parentheses grouped, okay? That's associative, okay? That's associative rule of algebra, okay? It works the same way in normal algebra, okay? And then what do? I do factoring, okay? I look at these two terms and go like, hey, they both have xi, ki. Why don't we factor that out? And then the yi is by itself over here, and then the not yi is also by itself over here. It's factoring, the reverse of distribution, right? Are we good so far? All right. Yep. Yep. So I do the same thing on the other side. And then this time I look at this and go like, hey, I know what that is because it is something or the negation of that something. Wait, if you have something which can be true or false or the negation of the same thing, then one of them has to be true. If at least one of them has to be true, the or has to be true as well, right? So that's how I simplify this to a 1 and also at the same time simplify that to a 1. The ones disappear because anything and true is just the original anything. And so now we are left with this portion and then do one more factoring step and then we end up with this term here. Okay? Then you look at this and go like, but Tech, we are not really that far away from where we started because ki plus 1 still depends on the k of I. Is that right? You look at ki plus 1 all the way here, and then you look at the end result here and say, hey, it still depends on k of I. I go like, well, maybe, maybe not. Okay? So this is also a place where most people will ask questions because the definition of the term g of I and the definition of the term p of I are here. Okay? They do not stand out, but it is important. Okay? So when you do your lab, which is the second lab, okay, the one that has to do with carry, look ahead, adder, you have to remember where to find the definitions of G and P. Is that okay? So I have already pointed out, okay, highlighted here, okay? So I just define G of I to be xi and yi. I define P of I to be xi or yi. Okay? Then we can re-express k of I plus 1 with simpler terms and just say, oh, it is the same thing as G of I or P of I and k of I. Do we have any questions of how we get to this part here? Are we good so far? Okay. So there's a reason why they call G and P. G stands for generate and P stands for propagate. Okay? So we'll go ahead and see what we can do with these terms over here. So the first thing we do is, okay, let's not talk about I plus 1. Let's make I 0 and see what happens. Okay? So we substitute that and goes like, oh, that's easy. Right? If I is 0, then K1 is G0 or P0 and K0. Does everybody see how we get that? Okay. Then we ask, what if I is 1? Well, if I is 1, then we first get to K of 2 is G of 1 or P of 1 and K of 1. That's just coming straight out of this part here. Then you go like, then we have a problem, right? We still have that dependency. But wait, we know what K1 is. We know what K1 is, right? So we substitute K1 being G0 or P0 and K0 into here. We expand it. Now there's no K1 anymore when we need to find out what K2 is. Is that okay? That is a nifty trick, okay? Extremely nifty. So in the second lab, the one that has to do with carry, look ahead, adder, you have to use the final form of each carry bit for consideration. Do not use just the first one. Okay? You have to use the final form of each carry. So now we look at K3, which is substituting 2 to I. Okay? So when I equals 2, what do we get? We get K3 equals to G2 or P2 and K2. Okay? That's just coming from the general equation. But at this point, we know what K2 is already. Yes? So we take what K2 is, which is this one here, and then we put it over here, and then we expand it using distribution, and we end up with this. Once again, K2 disappeared. Okay? Then somebody's going to say, yeah, but it's also longer. It's also more complicated. Isn't this going to take longer? What do you think? So we have to think about the number of level of gates we need to find the answer. Okay? There are gates like conjunctions. There are 4 input conjunctions. There are 5 input conjunctions, n input conjunctions that can take n inputs and do one single conjunction and get the output. And it takes, in theory, the same amount of time as a 2 input conjunction. Is that okay? So that means it will take the same amount of time to compute this, and also that, once we have the P's and the G's and the K0 ready. Are we doing okay so far? It will take one level of gate because P and G, they both depend on XY, which are the actual input, right? So it will take one level of gate to compute the P and the G terms. That one we cannot avoid. Okay? It will take another level of gate to compute the conjunctions within the disjunction. So now we have 2 levels of gate, right? And then we'll take the 3rd level of gate, which is the overall OR, to actually compute the OR of the entire thing. Is that okay? And that applies to K3, K2, K1, K100, because they will all have the same form. It's going to be a huge disjunction of conjunctions. And then in each conjunction, it will only involve P, K0, and G terms. In other words, using this method, the equation may look really ugly by the time you get to K64. Okay, it's going to be really long. It has 65 terms in it, and then the worst term of it has 63 terms by itself. But guess what? It would take, in theory, the same amount of time to compute. And it does not depend on the carry bit right before it. They only depend on the X, the Y, and the K0, which are all input pins. So are we getting the general idea of what carry look ahead is? It gets rid of the interdependency between the carry bits. Is that okay? So you look at this and go like, okay, Tech, I challenge you to give me K64. What does K64 look like? I'm not going to do it by hand. I'm not that dumb. I'm dumb, but I'm dumb enough to know I'm dumb. There's dumb, and then there's dumb. There's dumb enough not to realize that that person is dumb. Okay, I should stop. Okay, so this is the general equation. Okay, if you want to say, Tech, show me what is K64, then I'm going to tell you, substitute 63 as n and figure that out yourself. Okay, so you look at this and go like, we haven't even seen these symbols before. Well, they're very similar to sigma, okay, in the sense that this is a huge, gigantic OR, where there's an indexing variable I goes from 0 to n, okay, and each term that you are ORing in this gigantic disjunction is this portion. Is that okay? So when you look at that portion, you go like, well, the g of I we can easily figure out, okay, because that just depends on the index I. Then you look at this term here and go like, what is that? Well, this is a gigantic conjunction, okay? Remember that symbol is conjunction, is an and. So it's a gigantic and. Okay, what is in this and? Look at the indexing variable. It's j this time. Where do we start? We start from I plus 1. The I is already determined by the outer loop, so the inner loop can use I as a starting to determine where to start. So j is going to start with I plus 1, it ends with n, and then inside the conjunction, it's just a whole bunch of p terms. Is that okay? So you take the gigantic conjunction here and then just have one more and with the g of I. That becomes a single term of this gigantic disjunction. Is that okay? This part here is kind of separate. It is its own little term, which is k of 0 and basically p0 and p1 and p2 all the way up to p of n. Okay? So it is really the same kind of deal as sigma, except there's a little bit of nesting here. Yep, go ahead. Okay, so technically there's a open parenthesis here and a closed parenthesis over here. Yeah, so I just didn't write that. I can add that to my note, because I just use LaTeX to generate this. I can easily add extra parentheses to make that clear. But is that okay now? Okay. So, but this can be coded using C, C++, JavaScript, or whatever, right? So if your boss is asking you and go like, okay, I need to know the circuit of K64, of this 64-bit adder, you just write a program, okay? Double loop, string output, that sort of thing, and just have the program to figure out what that equation, what that formula or expression is going to look like. Is that okay? So it's very systematic. I mean, it doesn't look very difficult because, structurally speaking, it's not very difficult. It just looks ugly because there are a lot of terms. Is that okay? But because of this mechanism, and also because the level of gates stays the same regardless of which k we are talking about, all k bits can be computed at exactly the same time. They only take 3 propagation delays because there are only 3 levels of gate from the input pins to the individual k bit that we need. So now you don't have that dependency anymore. A 32-bit adder is going to take the same amount of time as a 64-bit adder. Is it going to use up more silicon? Oh yeah, it's going to use up quite a bit more silicon, but it still takes the same amount of time. So all modern processors make use of carry look ahead, which is this mechanism, instead of carry ripple, which is a very simple concept to explain. It works, but it is not practical because it takes too long. So are we good so far? All right. So we are going to transition to the lab right now. I'm going to clean up here, and then we'll walk over to the lab, and we'll have your lab start up.